begin. Right, um, so we're gonna be looking at some of the atmospheric contents of the green chemistry and environmental chemistry, which is in the module 3. And we're gonna start with the main thing we're looking at, all right, which is the ozone layer, all right. So with the atmosphere and truly, right? So the Earth's atmospheric ozone, right? Atmospheric ozone can exist, right, in the troposphere and in the stratosphere. And these are two main areas that we're going to be looking at, right? So the troposphere is close to the surface of the atmosphere, and the stratosphere is in the upper atmosphere, all right? Sorry, troposphere is close to the surface of the Earth, but close to the biosphere, while the stratosphere is in the upper atmosphere. All right. So we're looking at that. We're looking at the amount of ozone that is there, right? And we get this from UV spec as well, right? That's how we look at it. UV spec we used to get this type of data. All right. So we have a large copious amount of ozone in the stratosphere and just a little bit in the troposphere. All right. So we're just going to be looking at something like this. So the ozone layer absorbs 97% to 99% of the sun's incoming ultraviolet radiation. This is fundamental to protecting life on the Earth's surface from exposure to harmful levels of radiation, which can damage and disrupt DNA. All right. So we're looking at stuff like that. So in the 1970s to 80s, humans emitted large amounts of gases that depleted this ozone in the upper atmosphere as ozone concentrations in the stratosphere fell and a hole in the ozone layer opened up. There have been measurable increases in the amount of UVB radiation reaching the surface. Now, I'm a climate change activist, basically. Right? I'm basically an activist, right? So as it relates to things like these are the most important things that we have to look at as it relates to chemistry. And I think this is one of the most valuable things that we've got that we can get from chemistry too. Looking at the atmospheric impacts of these pollutants that we've been looking at or interacting with since module 1. Alright? Let's have a look at this. Right? So ozone formation is something that we must generally look at. So ozone, which is O3, right, is naturally formed, right, in the stratosphere, which is 20 to 50 kilometers above the Earth's surface, through processes driven by UV radiation from the sun. Right? So we have photodissociation reactions where light causes a breakdown of chemical bonds. So we have the photodissociation of oxygen. So oxygen is broken apart by UV light with bond energy of the oxygen double bond being 498 Kelvin per mole, kilojoules rather per mole, not Kelvin, kilojoules per mole. We're going to be breaking that bond there, right? And the energy of the UV light corresponds to the frequency of approximation of approximately 10 to the 15 hertz, which is within the UV range, right? So we're going to have a frequency of light of that many hertz, right? That will be breaking the oxygen double bond and splitting it into two different radicals. So I end up with O2 in the presence of UV light will give us two oxygen radicals, right? Then we're gonna have radical reactions. So the oxygen radicals now can then recombine with other oxygen molecules in two possible ways. First, they can recombine oxygen gas, right? Or they can combine to create ozone. So the oxygen radical can combine with another oxygen molecule to produce ozone, which is O3. This reaction typically occurs in the presence of a third molecule, usually oxygen gas or nitrogen gas, and that helps to stabilize the intermediate complex. Right? So the intermediate complex, which is a double radical, right, can be formed, and we need an additional molecule to basically stabilize that complex in order to produce ozone. Right? So ozone decomposition there. We're looking at something like that. So ozone molecules themselves also break down in the exposure of UV light. This decomposition process is similar to the formation process, but in reverse, and it leads to the release of oxygen atoms or oxygen radicals, right? So we have something there. So first, the UV light strikes an ozone molecule splitting off an oxygen atom, right? The free oxygen atom collides with O3, producing two molecules of O2. So this is the decomposition of ozone here. All right. So I have that molecule there. we're going to end up with a steady balance, right? We're going to end up with an equilibrium. So in the stratosphere, a dynamic balance exists between the formation and decomposition of ozone. All right. So we have that there. So the rate at which ozone is formed is balanced with the rate at which it is broken down by UV radiation. So this balance is going to be very important for maintaining our ozone layer, right? Or maintaining the concentration of ozone in the stratosphere, which plays an essential role in protecting the Earth from UV radiation. All right. So we're going to be looking at that. It is also important to note the ozone resonance forms, the structure of ozone, right? So we're going to have a double bond and a single bond. And we know that we're going to have a conjugate effect occurring, right? Resonance in the molecule occurring, right? As we have these two resonance forms. So we know really and truly that the true form of ozone exists as a hybrid form between these two resonance forms, right? So bringing you back to chemistry unit 1, module 2, or back into chemistry unit 2, module 1, right, where we look at the resonance forms, all right? So we have a system of delocalized electrons, and we know that when we have molecules that have double bonds and are rich in electrons, those are UV active. So we must remember these things. Also, electrons that are asymmetrically bounded, right, are also UV active. So with all our knowledge from module 1 and module 2, we must be able to look at things in module 3 and discern these properties. Alright? So the maintenance of ozone concentration via photodissociation. Alright? So we know that the ozone, stratospheric ozone is maintained by dynamic balances of formation and breakdown processes, right? So this is just a summary, right? So formation, the oxygen molecules absorb UVC radiation, right, and go through photodissociation. The oxygen atom now reacts rather with another oxygen gas molecule, right, and produces O3. And we also have this decomposition where the O3 breaks down back into O2 and the oxygen radical, right, or the oxygen atom, and the atomic oxygen now reacts with ozone to produce two molecules of oxygen. So this is a dynamic equilibrium which is established here, right? Oxygen molecule to ozone and ozone back to oxygen molecule. We must know these. The syllabus did state that we must look at it in terms of free radical substitutions, right? So we must know those. Must know it. Alright? So we have that there. So UVC radiation, right, is what is used to produce ozone, and UVB radiation is what is used to break it down. UVC radiation has a smaller wavelength than UVB radiation, which has a larger wavelength. Alright? So we're looking at stuff like that. Alright, so environmental significance of CFCs. CFCs are what we call chlorofluorocarbons, and these, go ahead. This one, the resonance one, or the one with the. Okay, so. Hold on, one moment. Alright, so what we're starting off with, right, is just oxygen, O2, right? And O2 is broken down into two oxygen radicals. Oh my gosh, what the heck is that? Right, so two oxygen radicals, right, through photodissociation. Photo meaning light, dissociation meaning it's breaking it. We have a, what is it, a homolytic or heterolytic cleavage? Which cleavage is this? Homolytic cleavage. So we have that type of cleavage in the presence of UVC radiation, right? So that causes that, right? Then one of these oxygens now are going to be reacting now with a O2. So we have O plus O2 will give us O3, right? So we end up with ozone. That's the photochemical reaction there, right? The photodissociation. Now for the decomposition of O3 now we do the reverse now. O3 now is now impacted by UV, this looks like a VV, but UVB radiation, and it produces now O2 plus O. Alright? That's what's happening there. Now when the one oxygen now is reacting with another molecule of ozone, it produces two oxygen molecules. Alright? So that's what it's saying. So UVC radiation breaks oxygen molecule down into individual atoms, right? And then one of those individual atoms react with the oxygen molecule to create O3, which is ozone. That is the formation. But with the decomposition now, we take the ozone and we use UVB radiation, break it into molecular oxygen and atomic oxygen, and then the atomic oxygen reacts with ozone to produces 2 moles or produce 2 moles, right, of the molecular oxygen. Right? So it's just something like that. So we must do the formation and the decomposition of ozone. Right? For this. The significance now of CFCs, chlorofluorocarbons now are the synthetic compounds that are commonly used as refrigerants, solvents, aerosols, or propellants, stuff like that. Right? So when we talk about fluorine industry, when we talk about chloroalkali industry, ammonium industry, ethanol industry, crude oil industry, iron and aluminium industry, all of these industries can produce harmful chemicals that produce chlorofluorocarbons, right? While these do not harm the ozone layer in the troposphere, which is a low atmosphere, once they reach the stratosphere, right? So please remember, if this is the land on Earth, right? So this is land, right? The troposphere is closer to the land, while the stratosphere is in the very upper reaches of the atmosphere, right? So what we're saying is that in the troposphere, these CFCs don't necessarily harm the ozone layer in that troposphere. But when we reach the stratosphere, way up there in the atmosphere, right, it then starts to cause harm. And that is because in the stratosphere, right, that is where we have most of the UV radiation interacting rather with the atmosphere. At the troposphere is not a lot of UV radiation reaching, but the stratosphere is basically the outskirts of the Earth's atmosphere that a lot of the sun's UV radiation is interacting, right? So in the stratosphere, it will harm, the CFCs will harm the ozone layer, right? So it's because they're chemically stable, right? And can persist in the atmosphere for a long time. But when it reaches the upper reaches of the atmosphere, which is the stratosphere, right, they can now break down by UV radiation and start interacting with ozone. That is what we need to get across here. Alright? So we're looking at stuff like this. So CFCs contribute to ozone depletion through a sequence, right, of reactions involving chlorine radicals. These reactions follow the typical initiation, propagation, termination mechanism for free radical substitution. So we know that mechanism. We know initiation, production of radicals. We know propagation is the production of radicals and stable species. And we know that termination is the production of stable species. We must remember those initiation, propagation, and termination mechanisms, right? It is the same thing for ozone depletion, right, in the presence of chlorofluorocarbons. Let's look at this. Let's use this CFC here. This is dichloro-difluoromethane, right? So we have UV radiation homolytic cleavage. In the stratosphere, UV radiation interacts with CFCs causing homolytic cleavage, right, at the weakest and most polar bonds in the molecule, which will be the chlorine carbon bond, right? Here, the weakest of them, all right? So we're going to have a bond breakage at the weakest area there, producing a chloride radical, right? So two radical species, a chloride radical and a chlorofluororadical. Do we understand what is happening here? What are radicals? Highly reactive neutral species. Lovely. Right? Moving on. Reaction with ozone now. So that was initiation. We'll produce radicals them now. Looking at this now. Propagation involves radical reacting with stable species to give radical unstable species. So now the chloride radical or chlorine radical reacts with ozone, leading to the formation of chlorine monoxide and an oxygen molecule. This step is the degradation of ozone. That is what we call this step, the degradation of ozone in the propagation. We have chlorine radical reacting with ozone produce chlorine monoxide and oxygen gas, or what we call molecular oxygen, or a oxygen molecule. There are many ways to talk the language of chemistry. Alright? So we have this here. Do we understand what is happening here? Lovely. Taking it step by step. Okay, so we start off with the chlorofluorocarbon, right? And when the chlorofluorocarbon reaches the stratosphere, we're going to have sufficient UV light interacting with the molecule. The UV light will now encourage homolytic cleavage at the weakest and most polar bond in the molecule. Whatever molecule it may be, chlorine carbon bond will be the weakest. Here, breaking at that bond, producing a chlorofluoro radical and a chloride radical. That is initiation. For propagation now, we have that chloride radical that was produced in the initiation step reacting with ozone. In propagation, we must show the depletion or the degradation of ozone. So we must show the radical reacting with ozone. So we have the chlorine radical reacting with ozone, leading to chlorine monoxide and molecular oxygen being produced. That is what's happening there. Clear so far? Clear so far? All right. All right. Okay. Propagation step now. Regeneration of chlorine. Notice, I give you guys these, because in propagation we must have at least three propagation steps. When you're showing free radical substitutions, you must show one or two initiation steps. You must show three propagation and a number of termination steps, right? So I gave you specifically three propagation steps. So one propagation step would be the degradation of ozone here. The next one is the regeneration of chlorine radical, right? So in this case now we have the chlorine monoxide radical, then reacts with another ozone molecule. This reaction breaks down another ozone molecule and regenerates the chlorine radical, making it a catalyst for the ozone depletion process. We're seeing that chlorine radical is a catalyst here. What is a catalyst? What aspect or characteristic of a catalyst that is displaying here? Lovely, it remains chemically unchanged at the end of the reaction. Beautiful. So the chloride radical is a catalyst in the depletion of ozone. So we must see that. So in the first propagation step, we show that the chlorine radical reacts with ozone to create the chlorine monoxide radical and oxygen molecules, right? And now the chlorine monoxide radical now reacts with another molecule of ozone to produce another chlorine radical, which is unchanged, and we end up with 2 moles of oxygen now, oxygen gas. All right, lovely. Last, alternate reaction with oxygen radicals now, right? So now, in this case, note that the formation and the decomposition of ozone is occurring in the stratosphere. We must remember that reaction from before. That is occurring at the same time as this reaction that we're talking about here. So in that reaction before, let's go back. Let's go back. Let's run back a little bit. In that reaction that we saw before, where is it? We saw that oxygen can be produced just atomic oxygen can be produced in photodissociation, right? Lovely. So let's type back here now. That oxygen that is produced in photodissociation can react with the chlorine monoxide, right? Radical, right? And now it can produce another chlorine radical and a molecule of oxygen. So you consider that is another propagation step. Propagation involves a radical reacting with a stable species to give a radical and a stable species. We have three. We have the reaction of chlorine radical with the ozone. We have a reaction of the chlorine monoxide radical with ozone. And we have the reaction of the chlorine monoxide with oxygen by itself. Atomic oxygen. Not molecular oxygen, but atomic oxygen. Right? So we have three propagation steps being shown here. Moving on to determination. Radical reactions or determination here. This process continues until two radicals, which is the chlorine and the chlorine monoxide radical, remains. These will now combine in a termination reaction, leading to the formation of a stable compound that no longer participates in the reaction sequence. This is now a dichlorooxide. Interesting. I thought that oxygen would be an anion and chlorine would be an anion, and now we have an entire complex here of an entire species with two chlorine and an oxygen. Let's look at this. Once this happens, the chlorine radical is removed from the catalytic cycle. But by this point, many ozone molecules have already broken down. So we know how propagation occurs. So this is occurring at a large scale throughout the atmosphere, right? As chemists, we must understand each individual reaction, right? But we must understand also that at the large scale of the entire atmosphere, this is occurring in the stratosphere, right? This is occurring over the entire planet, right? The breakdown of ozone due to our use of chlorofluorocarbons, right? Efficiency of chlorine catalysis, right? Each chlorine radical from a single CFC molecule can catalytically break down 100,000 ozone molecules before it is removed from the cycle via termination. This makes CFCs extremely harmful to the ozone layer, as a very small amount of chlorine can cause a significant depletion of ozone. So you see that chloralkali industry that we have, producing copious amount of chlorine for our uses in many different chemicals and different industries. When we use the chlorine, right, billions of tons of chlorine are released a year. And for every one dege chlorine radical, 100,000 ozone molecules are destroyed. So think about that impact of the ozone layer there. Ozone and human life. This is another aspect of the topic that our syllabus calls us to. The environmental and the anthropogenic impacts of ozone. So ozone in the stratosphere. So ozone in the stratosphere plays a crucial protective role in the Earth's atmosphere by absorbing harmful UV radiation from the sun. The ozone layer serves as a shield preventing excessive UV radiation from reaching the Earth's surface. So we already have a lot of UV radiation reaching the Earth's surface, right? Or already have a lot, right? So by us using these harmful chemicals and destroying the ozone layer, it doesn't help. We only increase the amount of radiation reaching the Earth's surface, right? We're gonna increase the temperature of the Earth as well. We're gonna increase the prevalence of skin cancers or other types of cancers as well, right? Because what UV light does, UV light can destroy and disconfigure DNA, and when it disconfigures DNA, what somatic cells will go through now is mitosis. So these now fundamentally flawed cells will continue to um, reproduce via mitosis, and those will now create tumors, etc. Right? So that is the development of cancer from UV radiation. Right? So we can look at stuff like that. The ozone is very critical, very crucial as it relates to the existence of life on this planet. So the absorption of UV radiation, the stratospheric ozone absorbs a significant portion of the sun's UV radiation, particularly particularly the harmful UVB and UVC types of UV radiation. All right. So the UV light is highly energetic and can cause significant damage to living organisms, including humans. So excessive exposure can lead to mutations in cells and tissue, increasing the risk of skin cancer, premature skin aging, and eye damage such as cataracts. All right. So we're looking at stuff like this. Health implications of ozone depletion is here as well, right? So when the ozone layer is depleted due to pollutants like CFCs, more UV radiation reaches the Earth's surface, increasing the risk of UV exposure that leads to high rates of skin cancer, incidence of cataracts, and weakened immune systems. Right? Vitamin D synthesis is also affected, right? So vitamin D, right, which we know to be dehydrocholesterol. Well, it has something to do with the dehydrocholesterol complex, right, which requires UVB radiation, right? Despite harmful effects of the excessive UV radiation, UVB radiation is essential for the production of vitamin D in the human body, right? UV radiation in the skin triggers a biochemical reaction to help convert a precursor molecule into vitamin D, which is crucial for bone health, immune function, and other bodily processes. Right? So looking at stuff like that. So it is important. About 90% of our body's vitamin D is produced via UVB exposure. Therefore, maintaining balance is important as effective UV exposure can be harmful. Excessive rather, UV exposure can be harmful. So even though the human body would use UVB radiation for a chemical reaction, right? We don't necessarily need a lot of it because too much of it now, right, would lead to skin cancers, etc., other deficiency, other things, right? But if we don't have enough UVB radiation reaching the Earth's surface, we're gonna lead to a deficiency in vitamin D. All right, so we're looking at stuff like that. Now, ozone in the troposphere. Now we know that troposphere is now closer to the ground, right? While ozone in the stratosphere is beneficial, ozone at ground level is the harmful pollutant, right? So we've been saying that ozone is good for this, ozone is good for that, but ozone can kill in high concentrations, right? So ozone in the troposphere is not naturally present, but it is formed through chemical reactions, primarily involving nitrogen oxides and volatile organic compounds (VOCs) in the presence of sunlight. Right? So when we look at burning of fossil fuels and using looking at the high proportion of the high rate of car usage, right? All those exhausts from cars and buses, etc. These release VOCs, right? That increase the concentration of ozone at the tropospheric level, right? It would make it have a secondary pollutant. Lovely. So we're looking at ozone. Ozone is a powerful respiratory irritant, right? Exposure to ozone can lead to a range of health problems, including asthma, right? Chronic obstructive pulmonary disease, increased respiratory infections, and cardiovascular diseases, right? So ozone can actually trigger these things. So it should be in the stratosphere. It should not be in the troposphere. All right. So we're looking at stuff like this. Contribution to photochemical smog as well. So photochemical smog, which occurs in urban and industrial areas, particularly in sunny days, right? We're looking at that. We're looking at how we can form photochemical smog using high proportion of ozone. So ozone is formed with nitrogen dioxide from vehicle emissions and other VOCs, right? In the other industrial sources react with VOCs. So we're looking at nitrogen dioxide and other oxides reacting with VOC in the presence of UV light. Right? So it results in the production of ozone and other harmful chemicals. Right? So this smog not only causes health problems but also harms the environment, including damaging crops, forests, and aquatic ecosystems. Right? So this picture here is just a city covered in photochemical smog. Right? So in highly industrious areas, right, we're gonna see the prevalence of photochemical smog. I think we look at the okay, so formation of ozone in the troposphere. Now, before we looked at the formation of ozone, that was for the stratosphere, stratospheric ozone. Now we're gonna look at the formation of ozone in the troposphere. Right? So we have the photolysis of nitrogen dioxide. So in the presence of UV light, nitrogen dioxide undergoes photolysis to form nitrogen oxide. So nitrogen monoxide, right? And a free oxygen atom. The oxygen atom now then reacts with oxygen molecules to form ozone. The ozone form then contributes to the smog formation and respiratory and cardiovascular issues associated with exposure. So this is really simple. That is it. That's the formation, right? So we're gonna have the photolysis of dioxide, nitrogen dioxide, right, releasing an oxygen atom that will now bind with gaseous oxygen to produce ozone. That is it. Let me pause for a second. Are there any questions, concerns, emotional outbursts? Is everything okay so far? All right. So I know I'm moving a little bit quickly, all right? But it must be done, all right? There's no rest for the wicked. It must be done. Yeah, I agree with that. I agree holistically with that. All right. The thing is, no, right? Once you, it's common sense in the way how if you've never seen the topic before, then you're gonna like definitely like fall out on the exam. But if you have like notions of what it is about, then you can common sense it through. So you need some of the information. You need to know about it. You need to be able to discuss it, and then you can go through it. All right. So that is that. So in summary, stratospheric ozone is essential for protecting life on Earth from harmful UV radiation, but tropospheric ozone is harmful, contributing to different issues, right? Particularly through the formation of photochemical smog. All right. So let me cut this recording right here. So we've gone through all of that so far, right? So the introduction